We go on with from exchange to the content models, and here Ian will start with the first content models.
Thank you. Good morning, everyone. Just share. Yeah, I'm going to speak a little bit about the part of the DATEX information model, road traffic data. Yeah, I'm talking about a full European standard published last year, part 5 of the EN 1615-7 series. It's called Measured and Elaborated Data Publications. We use the more concise name road traffic data as the name of the namespace in the DATEX 2 information model. And then for those of you who saw my discussion at the last webinar, where we split the specifications into quadrants, we're talking about the content side, and road traffic data it's a UML model, platform independent UML model, and it has technology specific realizations in the form of XML schemas and JSON schemas. And just to orient ourselves in the versions, road traffic data was added in release 3.1 made last year. So if you look for road traffic data in a DATEX 2 model, if you import the module, this is where it appears. You see in the hierarchy, it is a kind of, well, it's under the payload publication folder. It contains payload publications. And I think it's because DATEX 2 is modular, it's interesting to look at the namespace dependencies. If you want to implement road traffic data, what namespaces do you need? And it's only these ones. You need to use DATEX 2 location referencing, and you need to use DATEX 2 common. You don't need to use anything else. So you can use road traffic data independently from situation, VMS, and other publications. That's the top level contents of the road traffic data namespace. Some data types, classes, and enumerations as you'd expect, but we enter it through, on the left, 3 publication packages. And describing those, I'll start at the bottom. So measurement site table publication, that's really about static data describing measurement sites, traffic measurement sites, their equipment, their configuration, their positions, and so on, their static characteristics. And then you use that in conjunction with, when you have dynamic data to publish, you use a measured data publication. That contains the dynamic data produced by the measurement equipment that you have described in the measurement site table publication. If, on the other hand, you have traffic data that isn't really associated with any specific measurement equipment, you put that in an elaborated data publication. For example, one I tend to think of is a journey time produced by aggregating from individual floating vehicle data. So there's no specific measurement site which has produced that data. So you publish that in an elaborated data publication. So those are the 3 things you can do with road traffic data. So I'm just going to look at the top levels of each of these publications to just explain their contents a little more in terms of modeling constructs. On the left, we have the top levels of the measurement site table publication. On the right, the dynamic data, the measured data publication. Again, just the top levels with the details hidden, but just trying to focus on giving you understanding the shape of the classes. So the idea is that you make the static data publication, the constructs on the left, tell you what are your measurement sites and what are their locations. Then you come to publish the time varying dynamic data, and your measured data publication there on the right has a reference back to the measurement site table, so you can understand the connection. Each individual collection of site measurements has a reference back to the measurement site used to produce that. That's the basic pattern. One level down from that, looking inside a measurement site and inside a site measurements. If you had a very simple measurement site that only produced one kind of information, say it was a traffic count and that was all it produced, then the measurement site would have one measurement specific characteristics that would describe some properties, static properties, characteristics, fixed characteristics of that kind of measurement, that traffic count measurement. And then your site measurements with the dynamic data would just have one physical quantity with that count. But sometimes equipment will produce, the same equipment will produce multiple different kinds. It might produce, say, speed and count and occupancy, different kind of measurements from the one equipment at the one time. In that case, you have a number of measurement specific characteristics, one for each kind, and you have kind of mirrored parallel structure in the dynamic data where the site measurements has that many physical quantities, but all occurring at the same time. And contrasting that with elaborated data publication, no such constructs, you just go straight to having the physical quantities. Much of that pattern was the same in DATEX 2 version 2.3, but some changes in the details, and the physical quantity is a new concept. I'll explain a bit about that later. One more look into the static publication, just one more level again here, just to show that you can have different aspects of measurement specific characteristics. You can define, for example, your measurements may only be for a specific vehicle class, or you may have measurements from the one site that crosses multiple lanes and you have one measurement for each lane, or you may be classifying by axles, for example. So lots of different ways that you can characterize the measurements before you actually give the data. Going into the physical quantity, so it's where the different measured data and elaborated data publications they're uniform from here onwards, from the physical quantity. Now, the idea here is this was a construct introduced to try to allow efficient representation of data without having to repeat lots and lots of high-level wrapper elements, so that the XML or JSON, the payload, could be more concise, in particular for a time series. So if you know you have you may be publishing every few minutes, but you have a time series of measurements. Say you're publishing at 5 minutes and you have 5 1-minute data series, or even something more extreme where you have more data. In that case, you can use a time profiled physical quantity and have the individual data as basic data within this single time profile physical quantity, and avoid repeating all of the stuff that comes with the physical quantity and the constructs above. If you just have a single time to give and you're giving it as soon as it appears, then you use a single physical quantity which just has one basic data. The physical quantity can have a location because it might be different from the measurement site that created the location, or indeed it could be an elaborated item which didn't come from a measurement site, and various other metadata. So let's look at basic data briefly. There can be a lot, so we're getting closer and closer to the payload traffic data values now, the numbers. Basic data is abstract, but as you can see, there are different kinds. Weather data, which is itself abstract, and there are about 10 different concrete kinds of weather numbers you can give. Travel times, traffic status, and traffic data, which is a grouping including the concrete values of things like traffic speed, flow, gap, headway, density, occupancy, and even individual vehicle data. So we can give a time. Well, we should give a time for the data. Last pattern I have to explain, just one last design feature before I finish this quick tour of the road traffic data model. On the left, we see basic data, which are the things included Going back, the things included in a physical quantity. On the right, we see the data value, which is typically where the numbers really appear. And the reason for this split is what this diagram is trying to show. The reason why there are so many constructs and you just don't get numbers and not much else. The data value class allows you to specify various kind of quality indicators that have been computed dynamically for that data, like how many values have been used to create this one payload data value, or is there any information about the specific accuracy here, that kind of thing. So if you have a kind of traffic data value for which those kind of statistical properties are, or quality properties are relevant, then we've used data value concrete subclasses to represent that, so that you always can get, you have the option of giving these quality attributes. If, however, there may be some other kinds of data, such as a basic trend of increasing or steady or decreasing, that these numeric attributes in data value don't really add any significant value. We wouldn't tend to use them, and so they can go directly in the concrete basic data. So it's trying to explain the rationale for why we choose some basic data. So we tend to get patterns emerging like this one, and this is my last slide, but we tend to get patterns like we have a traffic flow. It's a container class. It's a kind of traffic data, which is a kind of basic data for those keeping up, which you get included in a physical quantity. Then the payloads are in specific data value subclasses for specific kinds of flow. Like you might want to give, you might be able to give all of these if you have the measurement equipment set up that way. You might be able to give axle flow, PCU equivalent flow value, percentage value, vehicle flow. Anyway, because these are data value subclasses, these inherit all the quality attributes, so you can give individual quality. That's optional. If you don't have any, you can just have an empty, well, not empty, you've got the payload always. This is like a percentage value, has to have the percentage, but the attributes you saw in the data value class would be optional. Yeah, so that was, I think, all I wanted to say about road traffic data, just giving you a quick tour of some of the design features, and I'll pass on to the next speaker.
So this is about VMS, variable message sign. What is was the publication of variable message sign through DATEX 2 aims to in DATEX 2. The scope of VMS message information delivery may be about this deliver information VMS messages status information among center for information delivery and also for traffic management function support. It is based on two publications. As we see in the road traffic data, we have a table which gives the identification and the static characteristics of the variable message signs, and the VMS status publication, which deliver the dynamic information, working status, dynamic characteristics, and setting, and displayed message. Let's go through the VMS characteristics and definition. And we have a view of VMS definition. Variable message sign is a display panel used to display one or more messages, text, symbol, pictogram, or combination that can be changed or switched on or off as required. Here are some examples of the VMS. These are structured VMS with specifically designed components for textual information and pictograms. So text and two pictograms, only text, only pictogram, compound pictogram and text part for management of different zones, for instance, for lane control system in dynamic lane management, tunnel management as well with traffic lights for lane traffic lights for the tunnel, and the textual and pictogrammic information. and also other kind of lane management by pictograms. It's not finished. We have also this kind of devices that are mobile devices. There can be some information, graphical information, mixed with text and signs, or information about the travel times, which have a dynamic part, a graphical part, like a synoptic map with coloring and text. But these are more specific tailored pictogram, of course. The trend is the VMS evolution based on full matrix technology, and which allow to have a total full matrix pattern which may be managed totally dynamically with pictogram or textual information in any combination. These are two examples of the German usage of this kind of VMS. It could be a challenge to design such a heterogeneous pattern of devices. But we have dealt into this through many meetings and harmonization phases, and we have now today a model which include all this kind of information. We should add also some further special purpose VMS, for instance, for parking and information, and fuel information, which are used along the road network. So keep this in mind. The VMS model structure is based on two main publications, which is VMS table for static data and VMS publication for the dynamic data. There are other packages for the different classes and specialized information that is needed: VMS configuration, fault, message, status, and graphic data dictionary. And also a bunch of enumeration. There are same dependencies. VMS depends on the common and location referencing namespace. And because of the messages, which are, there is a note here, because of the messages we may derive from a situation publication, we also have a dependency with the situation publication package, which is dependent if you include or not this kind of information in your model. Let's start with the VMS table. VMS table is based on a VMS controller table, really. VMS controller are the controller units which manages one or more VMS. VMS controller, as the table, are version identifiable to allow version management and updates. VMS are indexed. There is an indexed relationship. So a VMS controller as manages their VMS through this index, which are then identified by the VMS controller identification and this index. VMS, so the VMS control and VMS characteristics. We have static characteristics about design characteristics, kind of VMS type, and dedicated usage, for instance, for fuel information, lane control system, parking information, and so on. These are static information associated with the VMS. They have, VMS may have a location, of course, and may have a managed logical location. May have because we have also dynamic mobile VMS, which may be moved from one location to another. So VMS location may not be instantiated when in a static table, but only as a dynamic information. And there is a configuration as well that we will go we go to see. This configuration may be for parameters which are both static or dynamic in the when linked in the VMS publication. So in the VMS table publication, we will reference the static information. This VMS configuration is very, very important. We need to understand how a VMS is compound of display areas. A display area may be of a text display area, a pictogram display area, or a supplementary panel area. And these are indexed as the VMS was by the controller. These are the area are indexed one after the other. They all have a geometry information, dimension, and relative position among the different display area, and general position absolute to the VMS. And display area may refer to a specific lane as well. The same index that we use in a display area will be used as a reference in the VMS message setting. So when we will address a display area setting, the VMS message, we refer to this display area index. How do we manage this index and the display area positioning? There is a convention we assume, of course. If we have this text display on pictogram, the standard VMS pictogram and text are managed by left to right. 1, 2, 1, 2, 3, 1, 2, 3. If we have such a position to pictogram, if we have a vertical position, is up to bottom. Let's see how this can be applied in a more complex full matrix VMS. We take this example and we identify different areas managed with different textual or pictogrammic information. And these are all the numbering up, left to right, and up to above, up to down. So 1, 2, 3, 4, 5, 6, 7, and so on. So this is a conventional assumption, but the information about the absolute position and the relative position among the different areas are managed in the data model. So anything is possible. Let's go to the information, dynamic information of VMS publication. We have a VMS controller status, which are now giving the information of fault for both the VMS controller or the VMS status, is a general fault, and important, a working status, the overall VMS working status, which are blank, covered when the VMS is not in use, not working, and working. So this is mostly important for general in the understanding how the information can be delivered. Is the VMS is working or not? The dynamic setting, we have a VMS status. So we start with the VMS status here, going through. VMS status manage the location. We have a location that can be override the static location, or can be the mobile VMS location initiated. And it is more physical and the managed logical location. Then we can have messages, some more general flashing lights on general VMS information, and then the messages. Messages are VMS indexed as 1 to n to many messages may be associated to a VMS, and this index is used to refer which message. There could be also a dynamic configuration, which for full matrix VMS may be used to define the real-time configuration of the VMS for which the message is managed. Let's go then through the message composition. Message addresses the display area setting. So as we knew from the configuration, the VMS message related to the display area setting. The VMS has other information which are about the situation publication, the reason for setting, the message information type, and so on, which are general information of the management of the message. Then how the message is implemented is through the activation display of its display areas. And let's see how the display area setting works. This is the general information. Display area setting is related to the text display area, to the pictogram display area, or to the supplementary information display. This structure is the first level, is then assumed to have a lot of information. So let's focus to the text display area. The text display is simple, is a display area, a text display is compound of its line. The text line specifies the specific text used for each line. The pictogram display enables to deliver the pictogram which is displayed on the pictogram display area. And this is also simple, but we need to go through the pictogram after. The supplementary information display may either be of a supplementary text or a supplementary pictogram. And this may be instantiated, and it is also associated to a main pictogram. A supplementary information is supplementary to the pictogram display. We may have an image to show the pictogram as it is, the pictogram display as is set, and this is maybe some information, useful information to rendering. The last information that we need to assess in this for the display area setting is the multi-page display. When a display shows more than one page, this is through this association. So we generate a display area setting for a multi-page display, which will have associated for each page number different pictogram or text display based on the display area which are related, which we are describing. And so this mechanism may be very complex from this point of view, because it includes and it allows to deliver more information of a display setting for text, pictogram, supplementary, multi-page display. But when we can use this in a specific tailored for specific VMS model, simplified VMS model that we can have in our road network, we can profile the model and we can allow for simplified information description, and schema generated could be more simple, of course. But this modeling allows for the fullest flexibility and full management of all kinds of VMS, heterogeneous VMS we had described before. Let's go through the pictogram class. Pictogram class is interesting because pictogram is the pictorial part of the information representing the road sign, and it could be a regular pictogram, normally referred to GDD. GDD is the ISO coding of road sign. A regular pictogram is a simple pictogram. We also allow for composite pictogram. Composite pictogram is a compound image of a graphical image representing a location detail, for instance, the exit. In the next exit, there will be road work in this pictogram, so there is a condition of the pictogram, which say the location of the exit or the next exit, and the information of the situation. So it is associated to the regular pictogram as well. Some pictogram may also display a numerical information like as weight. GDD structure, and we are at the end.
Fabrizio,
we are, yes.
Yeah, please could you speed up a bit?
Yes, we are at the end. Yes, we are out of the more of the end. This is the GDD structure. The GDD structure allows to deliver the coding as in ISO road sign data dictionary specification. And this is the last, because at the end, when we have the VMS, the XML for the VMS encoded, these are the result. So we can deliver the VMS message through the text page and the pictogram display and the compound, for instance, 2 sequenced pictogram, 1 text line. And so at the end, you can see the easy, despite the model is very articulated, very structured, this is the information that we manage in XML. And so the model is huge and complex, but with guidance, the XSD schema is very flexible and the management of VMS information may be done in a very efficient way. Thanks.